Dr. Jill Tarter, Here and Now a Century Later. Tarter, to figure out how to find life beyond Earth, we need to put life on Earth into a larger context. It requires us to rethink what we mean by here and now. So what do we mean by here? That's simple. Most of us are working from home. In my case, on Shasta Road. In the Berkeley Hills. In the San Francisco Bay Area. From the altitude of low Earth orbit, we understand that I am here on the west coast of the U.S. Since 1968, when astronaut Bill Anders took this Christmas Eve photo of Earthrise, we've been able to envision ourselves here. This was our first opportunity for a truly cosmic perspective. It changed how we see ourselves and became the emblem of the environmental movement. In the summer of 2013, the Cassini spacecraft orbiting Saturn looked back and saw us, here. I hope you got the memo and went outside in your best clothes to wave at Cassini and participated in this selfie. Long before that, in 1990, the Voyager 1 spacecraft passed by Neptune and turned homeward to image our pale blue dot here. We are here, in the boondocks of a large spiral galaxy, far from the center. Our Sun is only one of 400 billion stars in the Milky Way galaxy. And no, this is not an image of the Milky Way since we cannot get outside of it to take such a picture. It's an image of a large spiral galaxy that is what we think the Milky Way would look like if we could go take a picture. Though we can't get outside to take a picture of the Milky Way, we can use radio telescopes to observe methanol and CO gases surrounding newly forming stars to map the Milky Way from the inside out. That's just been done, and here's our best estimate of what the Milky Way galaxy would look like from a distance. And our Milky Way galaxy is here. Only one of 200 billion galaxies in the observable universe. Curtis may have been able to envision this fabulous deep-field image from the Hubble Space Telescope, but Shapley would have been overwhelmed. The fact that some of these galaxies are smaller and fainter than others makes us remember that as we look farther out in space, we are looking farther back in time. So our perspective must also encompass that we are now in the current epoch of the universe's 13.8 billion year continuing evolution from the Big Bang to big brains and beyond. I have to confess that even scientists are not yet completely comfortable with this larger context of here and now. We have in fact only directly observed about 4% of the total matter/energy density of the universe. Cosmologists struggle with dark matter, dark energy, and gravity itself. At the smallest scales and the earliest times, it is not yet possible to reconcile quantum mechanics and gravity. Still, this is the most self-consistent perspective of the here and now ever assembled, one that will undoubtedly be subject to future self-correction. We humans are intimately connected to these faraway events in space and time because we trace their lineage not just back 1 century to the Great Debate. Not just back through the multiple centuries of our families. Not just back through the millennia of human civilization with its buildings, its art, and its many experiments with governance. We trace our heritage, not just back over millions of years since we branched off from the apes. Not just back over the 2.4 billion years during which the Earth's atmosphere has been perfused with oxygen thanks to the photosynthetic labors of cyanobacteria. Not just back to the formation of the Sun and our solar system 4.568 billion years ago, but back beyond that another 4 to 5 million years to a giant molecular cloud contaminated by the winds of Wolf-Rayet stars and the debris of supernovae explosions. The iron atoms and the hemoglobin molecules of our blood, the calcium in our bones, and all the elements heavier than helium that make you, were fused long ago, deep within massive stars that ended their lives in catastrophic convulsions, leaving behind remnants like this recent example. Remnants that became incorporated into our early solar system, just as this modern supernova remnant will be incorporated into a future generation of stars, and planets, and perhaps, life. We have learned that it literally takes a cosmos to make a human. None of this nucleosynthesis and cosmic connection story occupied the world of Shapley and Curtis, but their debate was a baby step along the path of discovery we think we understand today. It has taken millennia for humans to piece together this story, and today we still continue on our journey to understand more. We are driven on by curiosity about who we are, why we are, what else there might be, and of course, who else there might be. Over my own career, there have been 2 incredible game changers that have altered the course of our journey: extremophiles and exoplanets. Extremophiles, life as we did not know it until a few decades ago, thriving in places that we once thought completely hostile to life, are now illuminating the amazing possibilities for life on our own planet and perhaps elsewhere within our solar system and out into the cosmos. Today, thanks to the Kepler spacecraft and ground-based observations, we can say with statistical certainty that there are more planets than stars in our Milky Way galaxy, and that there is more potentially habitable real estate than we ever imagined. The missions capable of finding life by looking for biosignatures, the chemical fingerprints of life, on planets and moons of our own solar system and in atmospheres of exoplanets are now on the drawing board. The upcoming decadal review of astronomy and astrophysics for the 2030s will have a great deal to say on that subject. At the moment, we can only say that telescopes capable of imaging exoplanets and spectroscopically examining their atmospheres will be big. They cannot do their job otherwise. A lot of research is going on within the astrobiology community to understand what might be the best candidate biosignatures and how to interpret them and recognize false positives. There is a great deal yet to be known. Searches for technosignatures face the same problems as searches for biosignatures. They must deal with false positives and the difficulty of conceiving and building instruments to find what we don't yet know. Despite the difficulties, this type of research absolutely belongs within the portfolio of searches for life beyond Earth. Although this exploration has been called SETI, the search for extraterrestrial intelligence, in reality and in the future we will refer to it as a search for extraterrestrial technologies, or technosignatures. SETI applies the tools of astronomy to the search for evidence of technology elsewhere in the universe. Our own technology is visible over interstellar distances, and their technologies may be as well. A vast communications network, a shield against asteroid impacts, a stellar system whose planets have been asteroid-neared to suit the needs/wants of its inhabitants, or even something entirely unforeseeable might generate signals at radio, optical, or infrared wavelengths that a determined program of searching might discover. Historically, searches for signals from intelligent civilizations have been restricted to the radio and optical domains to listen and look for signs of someone else's technology. But recently Shelley Wright started working in near-infrared light to extend the reach of optical SETI, OSITI, farther through the dusty interstellar medium. Searches in the radio look for signals characterized by frequency compression. They look for patterns in frequency and time that indicate engineered signals, not natural emissions. Without explanation, your eye can see the difference between spacecraft signals and background noise. Some OSITI searches also seek engineered signals in the form of steady, nearly monochromatic laser lines, but others look instead for extreme time compression short pulses of light. The flashing of a laser as a signal, or perhaps as a way to accelerate advanced space sails to a fraction of the speed of light, machine learning will soon allow us to look for more complex signals, but since our goal is to find engineered rather than astrophysical signals, we will necessarily be building our own instruments. None of these searches will succeed if technology is not stabilizing and long-lived. Ultimately, what will determine success or failure in SETI is the mean distance between technologies throughout the cosmos. Distance across space and distance across time. In order for two technological civilizations to be close enough within space and time during the 10 billion year history of our galaxy, longevity is a requirement. We are a very young technology in a very old universe. We don't yet know whether it is possible for technology to persist and become old. Professor Philip Morrison has called SETI as the archaeology of the future. The tyranny of light speed means that any detected signal traveling across the vast distances between the stars will tell us about their past, but the longevity demanded for that successful signal detection will inform us that we have the potential for a long future. If someone else has made it through, we too can survive our technological adolescence. We began our observational journey with radio telescopes almost 60 years ago, and we added an optical search at the beginning of this century. Yet we have sampled very little of the cosmos. Using the Earth's oceans as an analogy, and confining our search to electromagnetic signals, Webb searched only about 1/12 ounces glass from the Earth's oceans. Recently, students at Penn State redid the calculation of the search volume we've explored, and they concluded that we're now up to a small swimming pool's worth of ocean. The Allen Telescope Array, ATA, is the first telescope built from a large number of small dishes, linked together with a great deal of computing power in order to search for signals in near real time. This allows us to immediately follow up on any signals we detect in order to discriminate against interference from our own communications technologies. In the future, this array can grow more sensitive by adding more dishes and adding more computational horsepower. Until recently, the array observed stellar systems with known exoplanets across the quiet terrestrial microwave window from 1 to 10 GHz, where we have a clear radio view onto the cosmos. But now that we know that all stars have planets, in 2015, Yuri Milner and the Breakthrough Prize Foundation pledged $100 million over a decade to sponsor a SETI search called Breakthrough Listen. Instead of building their own telescopes, the Berkeley SETI Research Center is using these funds to rent time on existing telescopes that they are equipping with very wideband recording and digital signal processing equipment. To date, they have installed equipment on the Green Bank Telescope at the National Radio Astronomy Observatory, NRAO, in West Virginia, USA. Their observing strategy is to observe both broad and deep. The Parkes Telescope and NSW Australia. New optical detectors on the automated planet finder at Lick Observatory in San Jose. Recently, they have signed MOAs with the FAST antenna in China, the Meerkat array in South Africa, Jodrell Bank antenna, and the E. Merlin array in the UK. In time, similar instrumentation will be installed on these observatories to support the 10-year search goal of 1 million stars, the galactic plane, and the 100 nearest galaxies. In the meantime, there are other groups around the world conducting radio SETI searches. UC Berkeley's SETI at Home and Serendipity on the Arecibo telescope. In the Netherlands, LOFAR is looking for transients and SETI signals. In Italy, a program called SETI Italia uses a 64 meters antenna at Medicina. And at a student training facility near NASA's DSN in the Apple Valley of Southern California, students operate a sky survey. In the desert of Western Australia, the Malura Wide Field Array of Dipoles is growing at a rapid pace and has begun surveying the sky in the antisolar direction for low-frequency, transient signals. And recently, theoretical groups in the UK and Sweden have been contributing ideas for novel search strategies. Since the beginning of the 21st century, we've also been conducting SETI searches in the optical part of the spectrum. Instead of looking for narrowband radio signals generated by a distant technology, we look for very short, bright optical pulses generated by their lasers. This work takes place at a number of university observatories. At Harvard, they have built their own dedicated survey telescope to search 80% of the sky over time. Berkeley reanalyzes the radial velocity data acquired by hires on Keck, and observes with the automated planet finder at Lick to look for pulsed or continuous laser signals. An amateur small Boquete Ozity Observatory in Panama is routinely observing. A team is developing new near-infrared (NIR) instrumentation at Lick. The GHAT team at Penn State have been data mining the WISE IR spacecraft archives looking for stray heat emission from astroengineering projects such as Dyson spheres surrounding individual stars and Kardashev 3 galaxies. Shelley Wright at UCSD and Paul Horowitz at Harvard are collaborating to make a very wide field of view facility for Ozity and NIR SETI, with the goal of viewing enough of the sky to gain sensitivity to transient events. Laser SETI being developed by Elliot Gillum at the SETI Institute, with funding from an Indiegogo campaign. When complete, it will consist of 96 wide-field cameras and gratings at 12 observing sites around the globe. It will be the first time we've been able to look at all the sky, all the time, for bright optical pulses. First, 2.4 meters width. Coronagraph and Starshade Demo Hab X 4 to 8 meters UV Starshade 16 meters, images of exoplanets LUVOIR 10 to 16 meters UV plus O plus I.R. First chance for biosignatures. And here's a bold new idea that I find fascinating: a single-purpose telescope that could perhaps show us the beachfront real estate on Proxima b and search for atmospheric and land-based biosignatures. Ozity could succeed sooner by incorporating OIR detectors on larger and larger astronomical optical telescopes now under construction, and conducting commensal observations as well as performing archival searches on stored datasets, or by building SETI-specific observatories such as Laser SETI and PanaSETI to generate large area scans of the sky at O and near wavelengths looking for transients, and build more sophisticated detectors and beamformers on future international radio telescopes. China is currently commissioning FAST, and an international collaboration is planning for construction of the SKA, with a precursor, called Meerkat, in the Kalahari Desert of South Africa. If the decadal review is kind, we may ultimately be able to build NGLA spread over the U.S. Southwest with vastly improved sensitivity. Ultimately, It may turn out that we detect distant technologies by means of the IR waste heat from conversion of energy into work, and discover that the heat islands of megacities. SETI, or the search for technosignatures, is one way we could succeed in finding life beyond Earth, but along the way to that discovery, SETI has a very important job to do, a job that can influence our long future, even if no signal is ever found. The process of thinking about SETI, talking about SETI, listening to talks about SETI, and conducting a globally coordinated search, all act as a mirror that shows us ourselves from a new, cosmic perspective. A mirror that trivializes the differences among us. We all need to take on the responsibility of protecting us from ourselves. We need to think and act and organize ourselves globally, creating another reality in which we see ourselves as Earthlings. Tarter. The final word belongs to Caleb Scharf, the chair of the astrobiology department at Columbia University. On a finite world, a cosmic perspective isn't a luxury, it is a necessity.